Hey everybody, Dr. White here, talking about some more tricks for finding antiderivatives. This topic is trigonometric integrals. What they mean really is that you're going to lean heavily on your basic trig identities that you've learned from pre-calculus in order to make some substitutions to find antiderivatives. So let's just start off with some examples. What if you had to do the integral of sine cubed of x? You're not going to be able to use regular u substitution on that. If you try to let u equal to sine of x, then du would be cosine x dx, and there just aren't any cosines in there. But why not try to get some cosines in there? Why not take sine cubed of x and think of it as sine of x times sine squared of x? Why is that useful? Well, there's a trig identity in your head. Sine squared x plus cosine squared x is 1. So sine squared x can be thought of as 1 minus cosine squared x. That's what I'm doing here. I'm replacing two of the sine of x's, sine squared x, with 1 minus cosine squared x. That's the substitution that we have in mind. That's the kind of thing we're looking at in this section. Now, when we multiply the sine of x through, we get this. And that breaks into two integrals. One of them is just sine of x, and the other is cosine squared of x times minus sine x dx. The first integral is easy to get. The antiderivative of sine is minus cosine. The second integral, you can think in your mind or on paper if you like, whichever is most helpful, about the u substitution. U is cosine of x. Du would be minus sine of x dx, and then you would be looking here at exactly this, which comes out to u cubed over 3 for an antiderivative. So cosine cubed of x over 3. Tack on a plus c and you have the full family of antiderivatives that makes up the indefinite integral that you wanted to find. So that's the basic idea for problems of the initial that are like the initial example. You might have a trig function that's some power of a trig function. It's all alone by itself. But if you can mix in one of the derivatives of the trig function, then maybe you can solve pieces of your problem by substitution, u substitution. So let's try another example of this sort. Can we find an antiderivative for sine to the fourth of x, cosine fifth of x dx? So that looks pretty tough. I'm going to get some coffee while I think about it. Okay, I got the coffee on, and I was thinking about it, and I thought, wouldn't it be great if we had a bunch of sines and then just one cosine, which is the derivative of sine? Well, right now I got a bunch of cosines. I only like to have one. And so I write my cosine fifth as cosine to the fourth times cosine. And that cosine to the fourth is cosine squared squared. The reason I wanted to do that is that cosine squared is 1 minus sine squared. I can then square out 1 minus sine squared squared. And I can multiply through the sine to the fourth x into this. Also, multiply in the cosine of x into this. And I'll end up with a lot of terms. I'll have a sine to the fourth times this 1, and also a cosine x times that. So I'll have a sine to the fourth cosine x. This term here is going to get a sine to the fourth, and it's also going to get a cosine x, becoming minus 2 sine to the 6x cosine x. And this last term, sine to the fourth, is going to get another sine to the fourth times a cosine, becoming sine to the 8th cosine. And then I have sum and difference of functions. I can do the integral of sum and difference is difference of sum and integrals. And so I've got those three integrals to work on. Each one of them could be done with u substitution, letting u be sine of x and du be cosine x dx. Once you've got power of sine along with cosine, this u substitution is going to help you. And so you'll end up with this after you do the substitution and apply your power rules. Tack on a plus c, and you've got the full family of antiderivatives making up the indefinite integral that you wanted to find. So mixing is great, but you might be thinking, wait a minute, for this mixing to work, I had to have some odd powers like this. I could siphon off an even power and then use this identity, and I'd still be left with the thing that would be the derivative. Or this right here, there's an odd power of cosine, so I was able to siphon off an even power that would turn into sines, and I still have my derivative of the sines hanging around. But what about if it's just straight up even power? Like, what about sine squared of x? What are you going to do then? Well, that's tough. Let me get my coffee while I think about it. Well, this mixing thing is just not going to work now. I've got to try something different. And so I think back to my trig identities. And there were trig formulas for the sine and the cosine of sums of angles. And right there, I'm pointing at the cosine of the sum of angles x and y. It's cosine of x times cosine y minus sine x times sine y. Totally important trig identity, one that you really should have memorized from pre-calculus. Now, if you let x and y be the same, like if you let them both be x, then you're looking at the cosine of 2x there on the left. That becomes the cosine of 2x. And on the right, you would have a cosine x times cosine x, which is cosine squared x, minus sine x sine y, which is the sine squared. We have a minus sine x sine x, which is a sine squared x. Now, looking at this expression, I'm just going to replace cosine squared with 1 minus sine squared. So I've really got cosine of 2x is 1 minus 2 sine squared of x. And I'm going to solve that for sine squared of x, getting the result that sine squared of x is 1 minus the cosine of twice x divided by 2. This is one of the so-called double angle formulas. There's one expressing sine squared in terms of cosine 2x. There's another one that expresses cosine squared in terms of cosine 2x that we'll meet in a minute. But my idea is to make this trigonometric substitution replace the sine squared x with the 1 minus cosine 2x over 2. We could break this fraction up into the two pieces, 1/2 minus 1/2 times the cosine of 2x. And integral of difference is difference of integrals. We're left with these two integral problems. The first one's pretty easy. It's just going to be 1/2 times x. The second one, I might need to think about a u substitution. Let u be 2x, and you'll eventually find that dx is du over 2. And when you work that through and take the antiderivative of cosine u, you've got sine of u for that. Replace u is 2x. Add on a plus c to get the full family of antiderivatives. And there we go. So great. That's how you could handle sine squared. Cosine squared x is 1 plus cosine 2x over 2. And it can be derived in the very same way, if you wish, except at this step here, instead of replacing the cosine squared with 1 minus sine squared, you might try replacing the sine squared with 1 minus cosine squared and then solve for cosine squared. So this too is an important double angle formula and ought to be memorized. You can use it to get the antiderivative of cosine squared. Same idea. Substitute, break up, use substitution. Now, you might think, well, what about like higher even powers, like the antiderivative of sine to the 4th x? Well, if we have an identity for sine squared x, maybe we could look for a way to apply it. Think of sine to the 4th x as sine squared squared. And then the sine squared, think of it as 1 minus cosine 2x over 2 double angle formula. You'll need to square this out. So you square out the top and you square out the bottom. And it's probably a good idea to break things up. So you break up into 3 fractions, the 1 over 4. And then the minus 2 over 4 becomes a minus 1/2 cosine of 2x. And then we've got a 1/4 cosine squared x. 3 new integral problems. One of them's really easy. This is just 1/4 x. Now here you're going to need a u substitution with u as 2x. But you'll quickly find 1/4 sine of 2x as the antiderivative. Now this one here might look like new and different. We know how to do cosine squared x, but how do you do cosine squared of 2x? You know? Well, you just use the double angle formula again, except in the double angle formula, wherever you see an x, put a 2x. You would then have cosine squared of 2x is 1 plus the cosine of 4x over 2. So let's give that a try, and we have this integral problem. But hey, we can break it up into the 1/2 plus the half cosine of 4x. And so the half, goes to x over 2. Cosine 4x is going to be a sine 4x over 4 after you do your u substitution. And so there's still a 2 that can come out, and now I've got an 8 on the bottom and this inside. So it looks like even powers of sine and even powers of cosine can be handled by getting down to the point where you use a double angle formula. So like you could try to treat sine to the 6 of x the same way. You could try to treat it as sine squared cubed. And then you have to cube out a bunch of stuff. That can get a little bit gnarly. So one alternative that the book suggests is, hey, integration by parts section, we actually found a reduction formula for sine to the n of x, and it works whether n is an even or an odd power. Here's that reduction formula in case you don't remember it from the last section. They prove it in the book in the last section. And you should feel free to use that instead if the powers are so high. And so this way you could start with sine to the 6th, and then you have to do a sine to the 4th, and you could use the reduction on sine to the 4th and get something involving sine squared, and you could even use the reduction on that, getting something involving sine to the 0, which is 1. You could work like that if you wished. Probably the most challenging thing might be when you've got sines and cosines multiplied together and there's even powers of each one of them. My suggestion, there's a couple of different things you can do, and my suggestion is go ahead and try to get even powers of just one type. So like if I see sine squared times cosine to the 4th, I'll turn the sine squared into 1 minus cosine squared, multiply out, and I'll have a cosine squared minus a cosine to the 6th. I'm sorry, I have a cosine to the 4th, 1 times cosine 4th, minus cosine squared times cosine to the 4th is cosine to the 6th. 2 integrals, but they're both even powers of cosine. So then what you need to do would be maybe appeal to the reduction formula for cosines, which they present in the textbook in this section. It can be proved with integration by parts, and gradually reduce each part down. So they completely solve this problem actually in the book as an example, and I'd recommend that you take a look at it so that you can make sure that you know how to do all of the record keeping that goes on when you use reduction formulas. As long as we're doing integrals with trigonometric functions, we should check to see are we okay with tangent and cotangents. I mean, we looked at sine a lot, we looked at cosine a lot. What about tangent? What about cotangent? Well, that's actually kind of okay and even done in previous sections. Because if you need the antiderivative of tangent, just remember its definition is sine over cosine, and try a u substitution where u is cosine. Then du is minus sine x dx, and there you are practically looking at du right in the face. You've got a minus 1 over u du, antiderivative log of the absolute value of u. We've done this in previous section. Similarly, for antiderivative of cotangent, which is cosine over sine, this time let u be sine, and you'll again get into a 1 over u situation. Log of absolute value of u is your antiderivative. So there are no new ideas to get those two integrals. We've actually already dealt with them in previous sections, previous chapters even. But what about stuff like secant and cosecant, the last two of the 6 basic trig functions? How would you get the antiderivative of secant of x? If you think of it with its definition as 1 over cosine of x, then you're seriously stuck. Try letting u be equal to cosine of x in a u substitution. The du, which is sine x dx, is nowhere there. But here is an incredible, clever trick. It's just amazing that this kind of stuff actually works sometimes. Take secant of x and multiply it by 1, but write 1 as secant x plus tangent x over secant x plus tangent x. You multiply by 1, so you have not changed what you're trying to integrate. But when you multiply through on the top and you compare it with the bottom, I notice, hey, you know the derivative of tangent x is secant squared x. And the derivative of secant x is secant tangent of x. The derivative of the bottom is the top. I could get myself into a 1 over u situation if I do a u substitution where u is secant x plus tangent x, the bottom. Du would be the derivative, secant x plus tangent x, plus secant squared of x, times dx. And so this integral here, all of this stuff is the du. The rest is 1 over u. And so we're looking at the log of the absolute value of u for our antiderivative. Plug the x's back in. Add on a plus c to get the full family of antiderivatives. Log of the absolute value of secant x plus tangent of x. What a clever move. I believe this was worked out in the late 1600s by one of the second generation of British mathematicians that worked on calculus. You could also do the integral of cosecant, similar trick, but multiply by 1 in the form of cosecant x plus cotangent x over cosecant x plus cotangent x. And when you multiply through and do the same kind of thinking, it works a very similar way. Now, there's a minus sign here because the derivative of cosecant is minus cosecant cotangent. The derivative of cotangent is minus cosecant squared. So that will be showing up here. What about like powers of tangent and cotangent and secant and cosecant? So the book has a couple of examples and suggestions for how to proceed there. I think I'll just content myself with, just showing you a small power of secant. And then we'll talk about like what you might do in more complex situations. So how about the antiderivative of secant cubed x dx? Well, I would like to somehow, could I possibly like mix secant with some of its derivatives, which would be secant tangent? Or some kind of mixture of powers of some trig function with the derivative of that trig function. So, like, I don't know what's going to happen here, but I know I need to do some breaking up. So I'm going to try letting secant cubed be secant times secant squared. And, you know, secant squared is the derivative of tangent. This is not a tangent sitting here. So this, I don't think I should try to do a u substitution at this point. I'm just going to give integration by parts a try and see if it helps me. I'm going to let u be the secant of x. So dv has to be everything else, secant squared x dx. So at least v I can get. It's the antiderivative of secant squared. It's tangent. And du would be secant x tangent x. So let me apply the integration by parts formula and see if I come up with anything easier. So here's my u times v minus my integral of my v du. Now here's my v, which is, here's my v, which is tangent. Here's my du. So I better take a look at this. I can put the tangents together, and I have secant times tangent squared. And that's not good. I can't think of this like as power of tangent. The derivative of tangent is secant squared, and I'm only seeing a secant. The derivative of secant is secant tangent, not tangent squared. That's not good. I don't see a u substitution way to tackle this problem. So I'll tell you what, let me see if I can just like get, you know, powers of one thing. What if I just write tangent squared as secant squared minus 1, which I can totally do. Because, you know, think about cosine squared plus sine squared is 1. If I divide both sides of this equation by cosine squared, I get a 1 here. I'd get a tangent squared here, and I'd get a 1 over cosine squared here, which is a secant squared by definition of secant. And so, actually, if I solved this for tangent squared, I would get secant squared minus 1. So I'm just going to like try that. I'm going to try that trigonometric substitution. Tangent squared is secant squared minus 1. And so then I'll multiply the secant x through here, and I'll get secant cubed minus secant. And I'll break those integrals up, and I've got, so far I've got my secant tangent minus the integral secant cubed plus the integral secant. Hey, integral secant, we know that's log of absolute value of secant x plus tangent x. We figured that out in the last example. So what do we got? We got this thing that we wanted to know, which is, and it's equal to this, which is like equal to this, which is equal to this. So the thing we want to know is equal to this. We have an equation involving the thing we want to know, antiderivative secant cubed x. We can solve that equation for the thing we want to know. I'm just going to add antiderivative of secant cubed x to both sides. I'll get twice the thing I want to know is all this other stuff about x that I know. I'll divide both sides by 2, and I'll get the thing that I want to know is this other stuff. Great, I've found an antiderivative for secant of x cubed. Add on a plus c, and I've got the full family, making the entire indefinite integral. So pretty amazing. Now, you know, what would you do for more complicated situations? I would tend to suggest reduction formulas, and the book is nice. They prove a few and introduce a few. If you check on the book, I'll see if I can just pull it up here somehow. Maybe if I minimize this. Here we go. Yeah, here's the book. Towards the end, they give you a table of trigonometric integrals. And some of it is just summarizing stuff we've already done, like, you know, the integral of sine squared or cosine squared, and some reduction formulas, sine of n, cosine n. Here's the tangent that we worked on. They don't show the cotangent. But notice, oh, here, yeah, they do show the cotangents right here. But notice they've got some reduction formulas you can use for higher powers of tangent, reductions for higher powers of cotangent. The secant we've worked out, I think you should memorize that one. It's so useful. And look here, here's a reduction formula to help you with higher powers of secant. Here's the cosecant that we worked out, and a reduction formula for higher powers of that. They even do an interesting discussion, which I think is optional. You don't have to read it if you don't want, of how to get integrals of sine of number times x times sine of another number times x. This is important in some branches of mathematics that you won't be looking at immediately. But it's interesting stuff. You can look at these last two if you like. So you can use those reduction formulas. Now, you might be thinking, so I'm just going to go ahead and just sort of address this with you. You might be thinking, well, what about like a machine? Couldn't it like do it for us? Oops, I'm trying to. Here we go. Couldn't you like go to Wolfram Alpha and like ask it to find antiderivatives for you? Like here, I went to Wolfram Alpha and I said, integral of secant cubed of x. And pow, it like popped out with it. It didn't pop out with the same thing we found, but it's programmed to like try out all kinds of tricks, use substitution, integration by parts, trigonometric substitutions of the sort that we're learning, and many more tricks that, some of which we will learn, and many more that we don't even have time to learn. And it employed some sequence of those tricks and got this expression here. Like, it solved it for us, or what if, what if you wanted to do, sine to the fourth of x times cosine to the, I don't know, 10th of x. So something would be horrible to try this by yourself. Can it get it? Wow, yeah, it can. And it would take us all day and night to get that using various reduction formulas. So you might wonder, like, why do we even learn these kinds of antiderivative tricks that we're studying here in Chapter 7 if a machine can do it better than us, a lot faster than us these days? And the reason is sort of twofold. One is, in actual more advanced math applications, when you're setting up models or developing theories, you're still going to have to think about how to find antiderivatives of certain functions. And you'll find yourself using integration by parts and use substitution, trig integrals, everything that we're learning. You'll find you're using it again and again and again. And the another reason is that just going through this process for a few simple problems like you're going to try in WebAssign itself, just going through that process solidifies some basic facts in trigonometry that you need in many contexts. These trig identities that you learned in pre-calculus and might have kind of mostly forgot, they are the lifeblood of a great deal of mathematics, and you're always going to be needing to use them. So here's a chance to practice them. And thirdly, it just generally teaches a very important set of problem-solving skills, because when you look at one of these tough problems and think, what should I do? Should I try to like mix something and its derivative? Should I maybe go for a reduction formula? Can I break this integral up into maybe some smaller integrals that each of them are easier? That kind of thinking, that problem-solving thinking, if you can learn it in one area, like mathematics, you can actually find yourself applying that same sort of resourceful strategic thinking in other areas that aren't even mathematics. So have at it and enjoy practicing problems from WebAssign in this section. That's all for now.